Hello. Today's class is today's lecture is on algorithmic differentiation. We have considered gradient descent and stochastic gradient descent and other ways to optimize our models to get to predictive or discriminative solutions. In all of them, if you recall, we needed a gradient of a function, and it was kind of assumed that we can obtain it somehow. And when you look at those derivations, when you look at the algorithm's explanations, of course, for analysis, we need the analytic form. And when we write down the gradient, it feels or may feel as if we absolutely need an analytic form to get a solution. In this lecture, we'll see that well, we'll just confirm that actually what we need is the numerical value, the number, the value of that gradient, all of its parameters at the particular input. And there is a way to efficiently calculate it. It's called algorithmic differentiation. As you see in this lecture, it's existed for quite a while. Uh, Let me see, more than 50 years for sure, 56 maybe. And it actually a lot of implementations of general use of algorithmic differentiation existed as well, but they weren't mainstream. Right now, most of you who've played with deep learning or worked with deep learning is using a small subset of algorithmic differentiation that works only for matrices and matrix computations. But the idea, the dream of with which the algorithmic differentiation was created is much grander. And although some languages that try to realize this dream and even get quite far along exist, they are not yet, unfortunately, mainstream. Okay, let's see what am I talking about? Let's see what we'll learn in this lecture today. Algorithmic differentiation. I will give you some overview and history, and then we'll talk about forward mode AD, forward mode algorithmic differentiation. Recall a little bit of backpropagation, and then talk about reverse mode AD as well. So let's start. Algorithmic differentiation, as Alexei Radul put it, may be one of the best scientific computing techniques you've never heard of. The very first computer science PhD dissertation introduced forward accumulation mode automatic differentiation, just so you know. 1964 by Wengert. So Robert Wengert published this paper, a simple automatic derivative evaluation program in communications of the ACM. And what he basically said is the key to the method is the composition of the given function into a series of elementary functional steps. Seems like this could be anything, right? But the community thought otherwise. Bellman, Kagiwara, and Kalaba, and Richard Bellman is of the dynamic programming fame, wrote a paper specifically, or report specifically titled Wengert's Numerical Method for Partial Derivatives, Orbit Determination, and Quasi-Linearization. So what did prompt them to write that paper specifically about Wengert's method? Well, importantly, when they say Wengert's method permits the treatment of large systems which might not otherwise be undertaken. So computational savings provided by the methods are huge, were huge at the time and still are. Well, so what is algorithmic or automatic differentiation, AD? Um, Automatic differentiation mechanically calculates the derivatives of functions expressed as computer programs at machine precision and with complexity guarantees. We will decipher all of that. We will open all of that soon. So automatically calculating derivatives is a dream that haunted Gottfried Leibniz and prompted him to create calculus in 1664. Um, the goal was to enable weak human brains with powerful tools, and by automating a lot. And as you know, Leibniz was also the one who invented binary calculus, but uh, binary numbers, and like thinking along the way how to automate everything. He also designed a complicated uh, calculation machine, but I'm not sure if he even built it. Well, anyways, so automatic differentiation. As you know, derivative of a function that maps from n-dimensional space to m-dimensional space is an m by n Jacobian matrix J, and we've considered that. We've seen that already. AD in the forward accumulation mode computes Jacobian times a vector, and uh, Wengert introduced that in 1964. AD in the reverse accumulation mode computes Jacobian transpose times some vector. Everything will become clear eventually in this lecture. And spill panning, Bert Spillpanning introduced that in 1980. This is basically solving the problem that the backpropagation currently solving, but actually doing it in a more principled way. So, and also about a zillion other modes and tricks exist for algorithmic differentiation. It's a vibrant field with regular workshops, conferences, and a community portal, AutoDiv. You can check it out for yourself. I will get you interested. So, what is AD? Automatic differentiation, also known as algorithmic differentiation, also known as computational differentiation. There are few modes or few flavors of it. So AD type 1, it's calculus for efficiently calculating derivatives of functions specified by a set of equations. AD type 2, it is a way of transforming a computer program implementing a numeric function to also efficiently calculate some derivatives. So think about your neural network. Your neural network in its forward path computes a number. So it implements a numeric function. But things like systems like PyTorch and others, they efficiently calculate the derivatives. So you on this forward pass, you add some complexity and you get some scaffolding for calculating the derivatives. We will go through that in this lecture a little bit. And there is also AD type 3. It's a computer program which automatically transforms an input computer program, another, specifying a numeric function into one that also efficiently calculates derivatives. So kind of complementary definitions or slightly overlapping definitions or different types of AD. So first of all, we need to define AD. We need to remove some confusions because I'm sure most of you who are listening to me now have confusions about differentiation and derivatives with respect to AD, especially because AD is not numerical differentiation. The language may make us think that it is numerical differentiation. But let's take this map. You can iterate through, start with L1 equals to some number x, and then keep iterating this map. At step 4, what you will get is this expression. If we go by numerical differentiation, we will either use left, right, or central approximation to the derivative. Basically, we'll define some h, and by using the definition of derivative as a limit of h goes to 0, it's the ratio of so increment in the function by the increment in the value, and if our step quite small, then we hope we will get a good approximation to the derivative, to the first derivative at least. So, well, it turns out numerical differentiation is a problematic approximation. It simultaneously commits two scenes of numerical computing, um, or numerical stability. So first scene or first commandment is thou shalt not add small numbers to big numbers. And yeah, so we are doing that, right? We are adding a small number to some large number. And another scene or another commandment that it's violating is thou shalt not subtract numbers which are approximately equal. Well, when we add a really tiny value to the argument, the function will not change much. So when we're subtracting two numbers which are approximately equal, we're violating both of these assumptions, right, one by one. So, but what is wrong with numerical differentiation? Besides what I just said, or opening it up a little bit. So there are two types of errors that happen in numerical differentiation. First one is truncation error, because we defined our derivative as first, like we took the infinite Taylor series, and we defined the derivative using only the first component of it, and whatever we threw away is our truncation error, and it is about so depending on where we truncate the series, and this error, even if we are at infinite precision, it still persists. So when h is largish, yeah, on the right here, 10 to the minus 3, when it's largish, truncation error is dominant. And here, this plot from the survey on mathematical differentiation that I'm heavily borrowing from in this lecture by Biden and others, shows central difference and forward difference to two types of approximation of the numerical approximation of derivative for numerical differentiation. As you see, up to some point, truncation error dominates, but then for central um, difference earlier and then for forward difference later, round of error kicks in and starts dominating the error. So round of error is when your precision in the mantissa, you need precision, such a high precision in order to maintain correct values that floating point numbers, number representation just are unable to hold numbers with the required precision, and error accumulates. So because in the tail of the mantissa there, the number are just noise. Um, so that is round of error. And while trying to get higher accuracy of your estimate by pushing this limit to zero, going to here, you are actually, well, on an infinite precision computer, you'd be fine, but on any computer that we have access to, well, those that we want to be fast, that are using numerical coprocessor or similar techniques. For those, yeah, we are in trouble, numerical issues. So just must be clear. Also, we did say, or I did say, and the definition did say that we get a numerical value of derivative at a numerical value of the input with machine precision. AD is not doing numerical differentiation, doesn't do this approximate derivative by differences. So it is also not doing what the symbolic differentiation would be doing. We're still considering that map at step 4, and what we could do, we could represent this map as a function f of x that returns this expression calculated, evaluated at these values. And then we could just take and manually say differentiate this expression and write a function that returns, evaluates this expression of the derivative. This is symbolic differentiation and it is exact, but imagine the need of differentiating symbolically like that, something like a transformer or network or a convolutional neural network or a recurrent neural network or something a large and complicated model with multiple moving pieces. So here's an example due to spill panning. Imagine that our function, a simpler example than a transformer, to see the problems with symbolic differentiation. Not just that, you have to do it by hand. You could say, we have those symbolic computation engines, Mathematica, Maple, and other derivative of maxima. Let's just plug it in, and it'll return for us some kind of symbolic solution. We don't care what it is. Well, usually what it does, symbolic differentiation, even though correct, it may be highly inefficient. It may create multiple terms that are not simplified or reduced, but there is even a more complicated problem, or well, you will see that it's not too complicated to show. Imagine that you need to to compute the gradient of this function, product of x's. And the gradient is nothing but df by dx1, df by dx2, and so on. So, well, product of all of the x's is differentiated by x1. It's everything, product of everything but x1. And then derivative with respect to x2, it's everything but x2, and then everything but x3, everything. Notice the redundancy. The redundancy is there. You keep computing same quantities all over and over again, d times. Well, yes, d times for the number of components. So this redundancy is a problem with symbolic differentiation, that it does not, basically it's inefficient. First, you have to run some kind of a solver, um, symbolic solver, that will return this or will return that. And then you have to either evaluate all of this every time, or again run some kind of optimizing compiler on top of that that will figure out the dependencies and will return a black box function that will evaluate the gradient for you in an optimal way. AD doesn't do that. AD does not give you symbolic differentiation. So what does AD do? What? Here's an example of a few functions. Those are polynomial, quadratic, cubic, and power 4. Those are just this is just a sine function, and this is a sine of x squared, and this is a tricky normalized exponent. The point, like I don't want to write the expression of it here, but the point is that I did plot it using a symbolic differentiation engine. I've used Mathematica to throw this together, and when our brains, with all of the years of education, are biased that what we want when we have the blue function, what we want is the orange function. We want the functional derivatives. But that's not always true, and mostly it is not true. When we're solving our gradient descent problem, t plus 1 equals wt minus the learning rate and the gradient with respect to w of some functional. So j, let's not use j because I've used it for Jacobian. Let's say it's the likelihood. This L function is this, right? But this function is already at some value of w at the previous value. So say we are here. When we're computing this update, we just need to know this value. We need to know this value, the value of the derivative. Where are we? 3. So let's say we are here. This is our old wt. That was a bad move. An old wt, and we have our function value at old wt with all of this, the old settings at this particular batch, sample, or whatever method you're using. So then we need this value, numerical value. And I'm specifically, of course, on purpose showing you very simple two-dimensional examples, but think of a multidimensional cases that is much harder. Well, you see why I'm mentioning that. But now you obtained here, okay, that is your gradient. Well, it's a number one-dimensional. So now take the w, the value of w, and make this step according to this gradient, to this magnitude. And you can show that most of the time, all you need when you are here in this function, you just need this particular number. That's all. You just need this number, or the full gradient vector, or the full Jacobian. But for update, you just need the gradient. That's all I want you to know as an introduction. Next section will unpack what the AD actually doing for us in one of the simpler ways.